All right, so next, let's talk about what happens if we have a subspace. And I'm going to try to just draw one as a plane here, like the span of two vectors, maybe. I'm going to call this W. And this is a subspace of Rn. All right, and then let's say I have just some random vector. Maybe this is my origin, this is the 0 vector, and I just have like some random vector just popping out here, and I'm going to call it y. And I want to figure out, how do I project this vector y so that it's laying on this plane, on this subspace? So I have a vector that's popping out, so it's not in the subspace, but I want to project it onto the subspace. So I'm going to try to draw something of similar length that is on the subspace. That's going to be my y hat, which we're going to be calling the projection onto W of y. Just like we did in the last section, but we're projecting onto a space. And we can do the same thing where we define an orthogonal vector, orthogonal to our projection, z. All right, so in today's lesson, we're going to talk about how do we come up with the formula for the projection of some vector onto a whole subspace, not just another vector. So let's get the definition. All right, so y hat equals the projection onto a subspace. All right, so projecting y onto a subspace of W. This is the orthogonal projection of y onto the subspace W. And our y hat is defined such that these two things are true. Number one, if you subtract our vector y and y hat, so this one minus this one, you're going to get something that is orthogonal to the whole space. So this z is not just orthogonal to a y hat, it's orthogonal to the whole subspace. And then number two, y hat is also known, so it is the unique vector in W closest to y. All right, so this y hat is, so if you think of W, the subspace having a bunch of, maybe infinitely many vectors inside of it, y hat is the one that's closest to y, which is not inside of it. All right, so that is, if you take the norm of y minus y hat, which is our z in that picture, that's always going to be less than the norm of y minus z. For all z, sorry, not z, v. For all v in W, with v not equal to y hat. It's going to be the closest thing to our vector y. All right, here's our note. So if we have a set of vectors, u1 to up, so if this is an orthogonal basis, all right, and so of W. All right, so that's a very convoluted statement. So let's break that down. This set of vectors is orthogonal. So if you dot product any two of them, you're going to get 0. It's also a basis of W, meaning that these are all linearly independent and they span all of W. So if this set of vectors is an orthogonal basis of W, then our projection, y hat, is actually the projection onto the first vector in our basis of y plus the projection onto our second basis all the way to the projection onto our last basis element. All right, so this gives us a way to define the projection of a vector onto a whole space. You first need an orthogonal basis of the space and then project our vector y onto each one of the basis elements and add that together. And that's going to be y hat. All right, so let's look at an example. Let's consider a subspace W in R3 where W is the span of these two vectors. 1, 3, -2, and 5, 1, 4. So this is like our U1 and our U2. All right, everything in W is going to be defined as a linear combination of these two. And also, we're going to define our vector y as 1, 3, 5. All right, so in order to use our note, we need to make sure that the things that make up this subspace is an orthogonal basis. So let's make sure these are orthogonal and linearly independent. All right, so note, if I dot product U1 and U2, I'm going to get 5 plus 3 minus 8, which is 0. That's great. So that means U1 and U2 is an orthogonal set. Also, these are not linear combinations of each other, so they're linearly independent. U1 and U2 is a linearly independent set. And we're using these to create all of W, so it definitely spans. So this set, U1, U2, is an orthogonal basis for W. All right, so knowing that we have an orthogonal basis, in the next video, we're actually going to find the projection of y onto this space.